Okay, let's unpack this a bit. It's always fascinating, finding mathematics in places you might not immediately expect.
Absolutely, like today's topic.
Exactly. So today we're doing a deep dive into some sources talking about fertilizer dynamics and also differential nutrient uptake in plants.
Right, quite specific. And looking at these, they seem really geared towards, say, college students.
Yeah, students who are probably studying math,
Mm.
specifically differentiation, maybe integration.
hmm Showing how these mathematical tools actually apply in the real world outside of the textbook example.
Right. So our mission here, let's say, is to really get a handle on how calculus, specifically differentiation, rates of change, is used to model something very concrete.
Like how a plant pulls nutrients from the soil.
Exactly. Over time.
Mhm.
What's happening right down to the root level, but described with math.
And what jumps out from these sources is that this uptake, it's not static, it's dynamic. Well, a plant doesn't just absorb nutrients steadily, like a vacuum cleaner. Its needs change. Nutrient availability in the soil fluctuates.
Ah, so the rate it absorbs them changes too, constantly.
Precisely, the rate of change. And that's the hook for calculus.
Okay, yeah, the rate of change.
Yeah.
That definitely sounds like differentiation territory if you're in a calc class.
It is. These sources really emphasize that. They show how you can use the derivative of a function to model the instantaneous rate.
Instantaneous rate.
Reform.
So how fast the plant is taking up a nutrient in any specific moment.
Exactly. If you imagine a function describing the total amount of nutrient absorbed up to a certain time, its derivative gives you that uptake speed or rate at that point in time.
Okay, I get that. But why is knowing the rate so important? Isn't the total amount taken up the main thing?
Well, yes and no. The total amount matters, of course, but understanding the rate, that tells you when things are happening most effectively.
Like when the plant is absorbing most efficiently.
Right. Or maybe when a nutrient is starting to run low in the soil compared to what the plant needs right then. It lets you understand the process, not just the end result.
I see. Moving beyond just inputs and outputs.
hmm And, these sources, they don't just stop with the derivative, do they?
No, seems like integration would naturally follow if you know the rate.
Exactly. Integration comes in as the reverse operation. If you have a model for the rate of uptake over time, you can integrate that function.
Then that gives you...
The total amount of nutrient the plant absorbed during a specific window of time.
Okay, so derivative is the speed, integration is the total distance covered. Sort of like that. But for nutrients.
That's a good analogy, yeah. Differentiation for the instantaneous rate, integration for the accumulated total over a period.
And I suppose it gets more complex. You add in things like soil temperature, moisture.
Absolutely. Those factors influence the rate. So you start building more sophisticated models, often involving differential equations.
Which basically describe how the rate of change itself is connected to, well, the current situation.
Precisely. How the rate depends on the amount already present, or temperature, or other factors.
Which, going back to those math students, is a pretty compelling reason why calculus matters.
Right.
You're not just solving abstract problems.
You're actually getting the tools to describe a living, dynamic system, a biological process, how a plant feeds itself, basically.
Using math to understand its interaction with the soil environment?
And if you think about the bigger picture these sources point towards applying these models, it can lead to smarter agriculture.
How so?
Well, maybe more efficient fertilizer use. Instead of just applying it broadly, you could time it better.
Time it to match when the plant's uptake rate is highest.
Potentially, yes. Or understand when nutrients are most likely to be lost, like washed away, to minimize runoff. Optimize growth by really understanding the dynamics.
So, wrapping this up for you listening, the main insight here, pulled from these sources, is really seeing how calculus fundamentals work in practice.
Right. The derivative gives you that instantaneous rate of nutrient uptake.
And integration lets you figure out the total accumulated amount over time.
And the significance of that. It's about having the mathematical language to actually model and understand these complex, dynamic soil-plant interactions. It's not just guesswork.
It allows for, more informed decisions in areas like sustainable farming.
Definitely. It shows how these math concepts, they unlock understanding.
It really grounds it, doesn't it? Thinking of differentiation as the speed of uptake, integration as the total consumed, makes calculus feel much more tangible.
So maybe a thought to leave you with. Consider the dynamic processes relevant to your interests or field. What's changing over time?
Yeah, could understanding the rate of that change or the total accumulation give you new perspectives?
Calculus might just be the key.